Today we're going to talk about justifying segment and angle relationships. Now, justifying just means that you're providing proof of the statements that you're making. Now, some of the justifications we are going to provide in these segment and angle relationship proofs are things like definitions, theorems, postulates, and properties of equality. Right? And you've seen some of those in the algebraic proofs that we've done this week. Now, many times proofs ask you to provide evidence of two figures being congruent. So let's quickly refresh ourselves on what it means for figures to be congruent. In general, we say that two figures that are congruent have the exact same size and shape. And here we see an example of this. We have two right triangles, and they all have the same side lengths. Leg lengths of 3 and 4, and a hypotenuse length of 5. So if I took this triangle here and performed some sort of combination of rotations or reflections or translations, I could fit it perfectly onto this triangle. Now, when we write congruent statements, we use this symbol right here. It looks like an equal sign, but it has this squiggly line above it. It's called a tilde. Some examples of congruent statements might be segment AB is congruent to segment CD, or angle 1 is congruent to angle 2. So let's define congruence in the context of segments and angles. So this is our first justification, the definition of congruence. And we can use this for both segments and angles. Segments are congruent if and only if their measures are equal. So these two segments are congruent. KA is congruent to segment TY if and only if the length of segment KA is equal to the length of segment TY. And because this is a definition, the converse is also true. We could start with this statement as our hypothesis and end with this statement as the conclusion. For example, if the measure of angle B is equal to the measure of angle C, then angle B is congruent to angle C. Remember that congruent statements are describing figures, like angles or segments, whereas these equations right here are describing some component of those figures. With segments, it's the length of the segment. With angles, it's the measure of the angle in degrees. Both of these are equations because they represent numbers. Now, here are some properties of congruence, or POCs, that you will often use with segments and angles. And some of these terms should sound familiar because they have properties of equality that represent the same sort of ideas. So in the middle, you'll see segments, and to the right of that, you'll see examples with angles. First is the reflexive property of congruence. For example, if we have this segment here within points AB, we can say that segment AB is congruent to segment AB. It's congruent to itself. And likewise, here we have angle 1. Angle 1 is congruent to angle 1. Now, you won't really see this property of congruence used in this chapter, but in the future, when we are writing proofs of congruent triangles, you're going to use this quite frequently. The second is the symmetric property of congruence. And the best way to remember this is that with symmetric property, we just switch sides. Symmetric, switch sides. So this says if segment AB is congruent to segment CD, then segment CD is congruent to segment AB, right? The statement is almost the same, except we're just switching the sides here. And here we see the same with angles. If angle 1 is congruent to angle 2, then angle 2 is congruent to angle 1. And the last one here is the transitive property of congruence. Okay, this says if segment AB is congruent to segment CD and segment CD is congruent to segment EF, then we can conclude that segment AB is congruent to segment EF. Right? The order is very important here. Notice that The conclusion, or the second part here, is the first part of our next statement. If angle 1 is congruent to angle 2, and angle 2 is congruent to angle 3, then angle 1 is congruent to angle 3. Now, one quick note that I want you to be aware of is that there is no substitution property of congruence. That's only for equations, in which we can use the substitution property of equality. So, if the order matters when using the transitive property, for example, angle 1 and angle 2, then angle 2 and angle 3, then angle 1 and 3. So the two, what they have in common, kind of has to be the middle names here. We might have to use this symmetric property to switch the sides so that our statements are in the correct order. So just be aware of that. Now let's look at some commonly used justifications used in proofs involving segments. The first is the segment addition postulate, or SAP for short. This says that if points A, B, and C are collinear, remember that collinear just means together on a line, all in the same line, then point B is between A and C if and only if the length of segment AB plus the length of segment BC is equal to the length of segment AC. And we've really already done this before, right? You have point B that's between two endpoints of a segment, so it divides that segment length into two shorter segments, whose sum is the length of the overall segment here, AC. But now we've just given a proper name to it, segment addition postulate, or SAP for short. Another very common justification with segments is the definition of a midpoint. This says that M is the midpoint of segment AB if and only if AB and M are collinear and segment AM is congruent to segment MB. I kind of went a little fast here and I put IFF. That's an abbreviation here for the phrase if and only if. So you can abbreviate that as IFF. And this tells us that segment AM is congruent to segment MB. So if we're told that M is the midpoint of segment AM or segment AB, then these two segments AM and MB are congruent. And you can use this in the other direction as well. If you're told that segment AM is congruent to segment MB and you're given this picture, then you can conclude that M is the midpoint. But you have to be careful here, because if you're not given a picture, then this statement alone is not enough to prove that M is the midpoint. For example, you could have a counterexample to that. In which case, we might have A and M and B, where AM and MB are congruent. But if I was to find the midpoint of AB, it would be somewhere right there. Right? So keep in mind that A, B, and M have to be collinear together. Now there are several more angle justifications than that for segments, and here are some of the most important. First, and this will sound a little bit familiar, here we have the angle addition postulate. Okay, it's pretty much the same concept as the segment addition postulate, except now we're dealing with angles. D is in the interior of angle ABC if and only if the measure of angle ABD, which is right here, plus the measure of angle DBC, which is right here, is equal to the measure of angle ABC, that overall angle. So we actually have three angles here, not just two. So if you see a picture like this, you can write this statement in your proof, and then your reason right next to it would be AAP, the angle addition postulate. Okay, next we have the definition of complementary angles. Two angles are complementary if and only if the sum of their measures equals 90 degrees. And this is only for two angles. 3 angles, 4 angles, 5 angles, etc. that add up to 90 are not complementary. It's only two. Angle A and angle B are complementary. If that statement is in your proof, or you're given that, then you can conclude that the measure of angle A plus the measure of angle B equals 90 degrees. If you're given this in your proof, then you can conclude that angle A and angle B are complementary. It works in both directions, right? If and only if tells us that these two statements are biconditional. Now, what usually goes with complementary, we then talk about supplementary angles. The definition of supplementary angles is that two angles are supplementary if and only if the sum of their measures equals 180 degrees. So complementary is 90, supplementary is 180. And we see the same setup here. Angles C and D are supplementary if and only if measure of angle C plus the measure of angle D equals 180. We could also say that the measure of angle C plus the measure of angle D equals 180 if and only if angles C and D are supplementary. Now, here are some more justifications that you'll see quite often dealing with angles, but these justifications tend to come in a group when you see them in proofs. So let's take a look at the first one. The definition of vertical angles. Well, our vertical angle definition, which we've discussed in the past, are two non-adjacent angles formed by two intersecting lines. So when you are given a figure that looks like this, you have some intersecting lines, there are two different pairs of vertical angles here. 1 and 3 are vertical angles, 2 and 4 are vertical angles. So when you're given a figure that looks like this, you can make one or both of these statements, and the justification would be the definition of vertical angles. Now, what's kind of the most important is that once you identify the angle pairing using the definition, you want to then make a conclusion about those vertical angles. And that is stated using the vertical angles theorem. If two angles are vertical, then their angles are congruent. So angle 1 and angle 3 are vertical angles. You can then say that angle 1 is congruent to angle 3. So you're going to state their congruence using the theorem. Now notice that this is not biconditional. If I wrote the converse of this, it would say if angles are congruent, then they are vertical. Well, two angles don't have to be vertical in order to be congruent. So this vertical angles theorem only works in this left to right direction. Another grouping of justifications you often see together is for another very common angle pairing, which is a linear pair. The definition of linear pair says a pair of adjacent angles with non-common sides that are opposite rays. So here we have these two angles that are adjacent to each other. Okay, quick refresh on adjacent definition. We have a common vertex, we have a common side, and we have no common interior points, so no overlapping here. But when these non-common sides just form a line or opposite rays, then here we have a linear pair. So just as before with vertical angles, when you're given a figure that looks like this, you can use the definition of linear pair to identify the pair of angles that are that linear pair. Now from there, we don't just want to stop at saying these are linear pairs, we want to start to make conclusions about them. And the first thing that we have to do is use the linear pair postulate. This says that if two angles form a linear pair, then the angles are supplementary. So once we've identified the angles as a linear pair, we can now state that those two angles are supplementary. And the justification, the reason, would be LPP, the linear pair postulate. And we've already talked about our definition of supplementary angles, but here it is again. If we have two angles that are said to be supplementary, we can conclude that the measure of those two angles' sum is 180. Now there are many justifications related to perpendicular lines and right angles, but we're just going to focus on a few for now. It's kind of the basics here. First, using the definition of perpendicular lines, and we use this upside down capital T as the symbol for perpendicular. Lines are perpendicular if and only if they intersect to form four right angles. So remember that lines extend infinitely. So if there are lines that are intersecting and not maybe segments, then we have four right angles that are formed. 1, 2, 3, and 4. So here, line N and line M are said to be perpendicular. So we can conclude that all four of those angles that are formed are right angles. And this is a definition, so it can work in the converse direction as well. If we're given this picture, but we're not told that they're perpendicular, instead we're told that these four angles are right angles, well, that means that these lines must be perpendicular. So once we have right angles, a lot of times we use the definition of right angles. This says an angle is right if and only if the measure of the angle equals 90 degrees. So if you're told that angle A is a right angle, sometimes we're given this symbol with the picture, you can then conclude that the measure of angle A equals 90 degrees. But because this is a definition, we can also use it in the other direction. If you're told that the measure of angle A, for example, is equal to 90 degrees, you can then conclude that angle A is a right angle. And if we're trying to prove that angles are congruent, a common theorem we might use is the right angle congruence theorem, which just simply states all right angles are congruent. So if you identify any two or more angles that are right angles, you can go ahead and say that those angles are congruent to each other by the right angles theorem. Well, now that we have a pretty good basis for justifications, let's work through a couple of examples. The first example, we are given that the length of segment AB is 12 and the length of segment AC, this full length right here, is 38. Now, let's say with this particular example, we are given all of the statements. Well, it's always a good idea to start with what you're given. AB is equal to 12, the length of segment AC is equal to 38. And our reason for writing this is always given. Next, we see the length of segment AB plus the length of segment BC is equal to the length of segment AC. That's our segment addition postulate, or SAP for short. Well, I have an AB here that's equal to 12, and I can now then replace or substitute AB with a 12. I have AC is equal to 38, so anywhere I see AC, like in the second statement, I can replace it with a 38. That's using the substitution property of equality. And now finally, to get BC by itself, we have to subtract 12 from both sides. It just becomes an algebra problem. So when you subtract a number from both sides, we're using the subtraction property of equality. And notice that what we're trying to prove, we've now written this statement, and so the proof is finished. It's completed. All right, let's look at one that deals with angles. Okay, we're provided with this picture here, and we're also told that the measure of angle 1 is 135 degrees. And we're told to prove that the measure of angle 2 equals 45 degrees. So let's go through the steps here. All right, we have our statements on the left and our reasons on the right. So here's our list of statements. Angle 1 and angle 2 are a linear pair. Now that's not given, but what I've done is I've looked at the picture, and based on the definition of linear pairs, I can identify these two angles, 1 and 2, as a linear pair. So when you're identifying angle pairings, you're using the definition. From there, I'm saying that angles 1 and 2 are supplementary. Well, that's due to the linear pair postulate, which says if two angles form a linear pair, then they're supplementary. Based on our definition of supplementary, I know that when I add the measures of angles 1 and 2 together, I should get a sum of 180 degrees, based on the definition of supplementary. Here I have the measure of angle 1 equals 135 degrees, right? Keep track of what you're given. Now, I could have put that as the very first statement and then used it much later. That's okay. But this is given to us, so our reason is given. In the next statement, I now take statement number 3, which looks very similar to statement number 5, except measure of angle 1 is being replaced with 35 degrees. 135 degrees, right? And I can do that because of statement 4, right? Anywhere I see a measure of angle 1, I can replace it, substitute in a 135 degrees. And so now I have 135 plus the measure of angle 2 equals 180 degrees. I use the substitution property of equality there. And last, to get the measure of angle 2 all by itself, we have to subtract this 135 degrees in order to move it over. So I use the subtraction property of equality. And that's when our proof is completed, right? Our proof statement matches this last statement here, so we know we're done. Now, these are not a full exhaustive list of justifications, but these are ones that will give you a really good basis and allow you to solve pretty much any of the proofs that you might see in this class.